page, we're actually looking at a completely different type of problem. We're no longer going to be having a numerical answer at the end. Rather, what we're going to do is we're going to try to verify that an equation is an identity. And so the difference between an equation and an identity, let me write it this way. Like 3x plus 1 is equal to 10. That's an equation, and it's going to be true for a specific number, right? If I solve this equation, I'm going to have 3x is equal to 9 first, because I'll subtract the 1 from both sides. And then I'll divide by 3, and I'll get x is equal to 3. Okay? So this is an equation. It's true when x is equal to 3. An identity is an expression that is true regardless of what values you put in there. So for example, if we take tangent of theta is equal to sine theta over cosine theta, this is true for any theta value. And not just for one value, it's for all values. And so because it's true for all values of theta, then we don't call it an equation, we call it an identity, or we call it more than just an equation. It's an identity. And so if they ask you to verify that an equation is an identity, what they're asking you to show is that this equality will be true regardless of what theta values you plug in. And so the way that we do it is we use previous identities. So we assume that these have already been proven to be true, and we use them to manipulate the expression that was given to us and trying to make one side look like the other. And so that's actually the very first tip that I've written up here for you guys to keep in mind, is that you want to start by either simplifying the left-hand side or the right-hand side of the equal sign, and then to arrive at the expression at the opposite side only. You never want to work on both sides at the same time, because then that means that you've already assumed that the equation is true, meaning that the equality will always be true. And if you're trying to prove something, you can't prove it by assuming that it's already true, right? You have to start at some point that is completely independent of the other side of the equation, and then arrive to that conclusion. So the second tip is to choose the uglier side, the uglier looking side. What that means is that you just want to choose the one maybe that has the most parentheses, or maybe that has like several secants and tangents and cotangents, because this is going to give you the most to work with, meaning it's going to give you the more possibilities of things that you can try. And the last one, just be creative. These problems tend to be the more difficult type of problems that students often express, struggling with. So just a lot of in the beginning, it's going to be a lot of trial and error. Okay, so don't feel discouraged if in the beginning, just like, if I'm not getting it, just keep trying new things, and then eventually you'll get an intuition for what works and what doesn't. All right, so let's apply those 3 tips to the following example. For part A, we have cotangent theta plus 1 equals cosecant theta times cosine theta plus sine theta. Okay, so in this case, the side that I would choose to begin simplifying would be the right-hand side. And by the way, RHS, I like to write right-hand side as RHS. Okay? So the right-hand side is this cosecant theta times cosine theta plus sine theta. And the reason why I'm starting here is because of the parentheses. I know how to simplify parentheses. I know that I can apply the distributive law to help me simplify that. So that's what I'm going to do here. I'm going to take the cosecant theta and distribute to both of these terms. So we're going to end up with cosecant theta times cosine theta, and then plus cosecant theta times sine theta. And I'll write my justification here. This is by distributive law. Okay, the next thing could be to think, what is it that I'm trying to get to? What is my goal? Well, my goal is to make it to the left-hand side, to get this to simplify to look like this. It means that I need to end up with a cotangent. And currently, I don't have anything that looks like a cotangent. So maybe the next thing would be to try and simplify the cosecant so that it no longer looks like cosecant, so that maybe it gets me a little closer to the cotangent. So what do I mean by that? Well, cosecant we know is 1 over sine of theta, right? And if you ever forget, you have these reciprocal identities up at the top on the left column as well. Okay, cosecant theta is 1 over sine theta. So that's what I'm going to write here. Cosecant theta is 1 over sine theta, and then I have the times cosine theta that I'm bringing down, plus 1 over sine theta, okay, that's for the cosecant, and then times sine theta that I'm bringing down. This is by the reciprocal identity for cosecant. Okay. Now what? Well, now I'm going to take this product. So this is like multiplying by a cosine over 1. Same with the sine here. That's like a sine over 1. So 1 times cosine will give us a cosine theta. Sine theta times 1 will give us sine theta. And then in the second term, 1 times sine will give us sine theta. And then sine theta times 1 will give us sine theta. Okay. Now, how does this simplify further? Well, again, look at your formulas and identity sheet. Cosine theta over sine theta is cotangent theta. Okay, so this becomes a cotangent, which is actually great news because that's one of the terms that I want to get. And then the sine theta over sine theta, that simplifies to a 1, right? Or if you like to think about it as cancels out, those cancel out to a 1. They divide out to 1. So we end up with the expression cotangent theta plus 1, which is precisely what our goal was. Okay, so this is equal to the left-hand side, which means that we have proven that this is an identity. The questions here, I'm going to just write the justification here. Is this okay? Let's take a look at part B. Okay, so for part B, we have tan squared x times 1 plus cotangent squared x is equal to 1 over 1 minus sine squared x. Okay, so we're in this case, we have the parentheses or the uglier looking side on the left-hand side, right? That gives us at least this distribution to work with. Whereas on the right-hand side, it's not very clear what we should do, right? And there's not too much that we could do to simplify this. So I'm going to start on the left-hand side. We're going to get, okay, so if I distribute, I'll write it on the second line so it looks a little cleaner. We're going to get a tan squared x times 1, which is tan squared x, plus a tan squared x times cotangent squared x. So that's distributing to that term there. All right. And maybe at this point we think, okay, now what? I don't know what to do from here. Well, maybe at least what we could do is write what tan squared x even means, right? Whenever we have a trig function squared and then the variable, that simply means first take tangent of the angle, in this case x, and then square the result. Same thing over here. We can take tan of x and then square the result, and then we have times cotangent of x and then square the result. Okay. And I forgot to write my justification here, so let me just write my justification. This is by a distributed law. And this is just by definition of square. Okay, now how does that help us? Well, maybe here there's not too much that we can do, but here we have the same factor receiving a power of 2, or I should say the two factors receiving the same power of 2. So what we can do then is there is a power law that says whenever you have a times b raised to some power n, that's the same thing as a to the n times b to the n, meaning each of them receives a power. So we're going to be using this law, but in reverse, because currently what we have is something like a to the n times b to the n. I'm going to write this as a times b, which would be the tan x times the cotangent x, and then the exponent all the way outside. And we'll see why in a second. But we're going to write it as tan x times cotangent x and the square outside. And this is just by the power rule for products. Okay. Now, why are we writing it this way? Well, remember what tan x and cotangent x are, and the reason that I'm saying that is I know I'm supposed to end up with just sine, but right now I'm looking for ways that I can get rid of the tan and the cotangent. And the first thing that pops in my head is to write tangent and cotangent in terms of sine and cosine, right? So tangent is the sine over cosine, and cotangent is the reciprocal of that. It's the cosine over the sine. So we're going to write that out. We're going to have sine theta over cosine theta. Oh, and I'll be careful here. This should be variable x. Okay, so sine x over cosine x squared plus sine x over cosine x times cosine x over sine x. And then we have squared. And this is going to be by the tangent and cotangent identities. Okay. Now look at what happens with the second term. The cosines cancel, the sines cancel. We end up with a sine. I'm going to apply this squared to the numerator and denominator now. We're going to end up with a sine squared over cosine squared x plus a 1 squared, which is simply just the 1. Okay, so what happened here? Here I applied the power rule for quotients. That power rule simply states that if you have a over b raised to some power n, that you can take a to the n over b to the n, meaning you can apply the power to each the numerator and denominator. And so that's what we've done here. We took the square and applied it to the sine, and then applied it to the cosine. Okay, so we're definitely getting closer to our goal because we no longer have a tangent and cotangent. But we're still not quite there yet because there's a cosine present and there is also more than one term, right? Here we only have one term. Here we have two terms, this one and this one. So we have to find a way to combine it into one term. So let me ask you this. What if I had a fraction that maybe looked like 4 over 3 plus 1. How would I combine that into one term?
Make one a fraction?
Yeah, make one a fraction, right? We would do that. We would say, okay, well, this is going to be 4/3 plus a 3 over 3, right? And how did I pick a 3 over 3? Well, we want the same denominator. So in this case, after I simplify this a little bit, so let me just rewrite it. This is sine squared x, cosine squared x, and then plus 1. If I want to combine these into one term, I need to have the same denominator. So I'm going to write this 1 as a cosine squared x over cosine squared x, right? Let's write that. We've got sine squared x over cosine squared x plus cosine squared x over cosine squared x. All right. So now that we have the same denominator, we can add across the numerators to get sine squared x plus cosine squared x all over same denominator, cosine squared x. Okay. Now, what we have one term, so closer to the goal, but not quite there yet. But we need the numerator to be 1. Okay. Currently, our numerator is this stuff. Do you guys see any identities that might help us with this problem? Anything that might make the numerator no longer look like sine squared plus cosine squared? Is there anything on there that looks like sine squared plus cosine squared? Yeah, good. Thank you, Martin. So Pythagorean identity. Take a look at the Pythagorean identities. There's 3 of them. The very first one has a sine squared theta plus cosine squared theta is equal to 1. And this is for any angle, right? As long as these 2 angles are the same, you take the sum, it will equal 1. So in our case, we have sine squared x plus cosine squared x, which is going to be a 1 over cosine squared x. And this is by Pythagorean identity. Okay. So we're a lot closer now, but we still have a different denominator. We have the cosine squared x. Okay. Let's see. I'm going to give you guys a hint for that last part. We have Pythagorean theorem is sine squared x plus cosine squared x is equal to 1. That's the identity. So what would cosine squared x be if we were to solve for it in this identity?
1 minus sine square x.
Exactly, good. Okay, so cosine squared x here would be 1 minus sine squared x. So we can actually use that same identity now to replace the cosine squared x. We would get 1 over 1 minus sine squared x. Again, by the same thing. And if we look up at the equation, we see that that is the right-hand side that we were trying to reach. Okay, so now at this point, we're done. Is equal to the right-hand side, which means we have an identity. Sometimes it takes several steps. It always helps if you ever get stuck on a step and you feel like I don't really know where to go from this point. Always go back to the goal. Always look back to the side that you're trying to reach and think about what would take me one step closer to that side. Okay, so like for instance, for us here, maybe at this point we would have been lost and think like, well, I can't really simplify this anymore. But then think, okay, why should I have 2 terms? The answer is supposed to be 1 term only. So maybe I can combine the 2 terms and see what happens from there. So 1 step at a time. Great. Any questions there? right, let's take a look at this next one. Now, for part C, both sides don't really have any parentheses, right? Let me see if I can place the focus on this. It looks a little tiny bit clearer. Okay, that's a little better. So whenever you don't have parentheses, we said maybe the next best thing is to work on the side that has the secants and the tangents and the cosecants, because at least then we know that we can replace sine and cosine into those expressions. So here I'm going to start on the left-hand side. And we said, let's go ahead and replace secant with 1 over cosine. That's the reciprocal identity. And the tangent with sine over cosine. Okay. Now, complex fractions, again, I'd like to deal with them early. So I'm going to multiply top and bottom by the least common denominator. The denominator in all of these is cosine. So we'll multiply by cosine alpha over cosine alpha. And then if you distribute to the first term in the numerator, then we can forget momentarily that the denominator exists. Okay, so just focus on this part. So if we distribute the cosine to 1 over cosine, these are going to cancel out and it's going to give you just the 1. Okay, so we're going to end up with a 1 plus, and then distribute the cosine into the sine A over cosine A, and these cosines are going to cancel, leaving you with just the sine. So we'll have a 1 plus sine of alpha. And the denominator is essentially the same thing, except we have a minus instead of a plus. So we can expect that this answer is going to be over 1 minus sine of alpha. All right, now let's think about what we are trying to reach. Okay, because maybe at this point we kind of have to pause and think, why there's nothing more I can simplify. I can't replace any more tans or secants or cosecants. What is it that I'm trying to get? Well, I'm trying to get to 1 plus 2 sine alpha plus sine squared alpha over cosine squared alpha. Let me tell you this. If we were to replace sine of alpha with y, okay, so if we let like y is equal to sine alpha, what would happen to this expression? We would get a 1 plus 2 times y, because that's the sine alpha, plus a sine alpha squared, so that would be plus y squared. Okay, so we get the expression. Normally we like to see these in decreasing order of the powers, so we would have a y squared plus 2y plus 1. What do you guys, does this look familiar? Y squared plus 2y plus 1, have you seen that before? This is something that perhaps in algebra came up often, right? And this is actually a perfect square trinomial. And perfect square trinomials mean that you can factor them into the product of a binomial with itself. So what it means is I can write this as a y plus 1 times a y plus 1, right? Do you guys notice that? Or remember that, I should say? So what I'm trying to do here then, okay, if y is representing the sine alpha, that means that this top part actually factors into a sine of alpha plus 1 times a sine of alpha plus 1. Now, how does that help us at all? Well, look at where we're at. We're here. We're at 1 plus sine alpha over 1 minus sine alpha. And we're trying to get to this, right? Because these two expressions are the same thing, except one is factored and the other one's not. So in order to go from this to this, what should I do to the numerator? Well, to numerator and denominator. I can't just do it to the numerator. But what should I do? What could be my next step? Well, this is one of those factors, right? It's just written in the opposite order. It's written as 1 plus sine alpha. But in plus, we don't really care about the order. 3 plus 2 is the same as 2 plus 3. So if I want to go from 1 plus sine alpha to this product of 2, I just have to multiply by another one. Okay, I just have to multiply by 1 plus sine alpha. But whatever I do to the numerator, I have to make sure that I do also to the denominator. Otherwise, I'm going to change the value of the fraction. And here I'm just multiplying by 1. Okay, so what happens when we do that? Well, that means that we're going to have to distribute. 1 times 1 will give me 1. 1 times sine alpha will give us 1 sine alpha. Sine alpha times 1 will give us sine alpha. And then sine alpha times sine alpha will give us a sine alpha squared. In the denominator, we have 1 times 1, which is 1. 1 times sine alpha, which is sine alpha. Negative sine alpha times 1, that's negative sine alpha. Negative sine alpha times sine alpha, that'll give us negative sine squared alpha. Okay. Oh, I forgot to change pen color. But these are going to cancel each other out. In the denominator, we'll just end up with a 1 minus sine squared alpha. In the numerator, these two are going to combine. And we're going to have a 1 plus 2 sine alpha plus sine squared alpha. Okay. Now look at the goal. Okay, the right-hand side is our goal. The numerator is exactly the same, which means it's only the denominator that needs some type of manipulation for now. Yeah, so what can we do about the denominator? Well, we've actually kind of already done in another problem.
Pythagorean theorem or Pythagorean identity.
Good, yeah, excellent. So Pythagorean identity. If you recall, let me bring back well, actually, I think I just have to flip the sheet. The Pythagorean identity was this sine squared x plus cosine squared x equals 1. If we solve for the cosine squared, we'll get a 1 minus sine squared. So that's what we're going to do here. Instead, we're going to have the 1 minus sine squared replaced with cosine, right? So with cosine squared. So 1 plus 2 sine alpha plus sine squared alpha is numerator. Denominator becomes cosine squared alpha. And this is by Pythagorean identity. And I'll write it here so that, again, we see what was done. The original identity is this. And then if we solve for cosine squared, that means we have a 1 minus sine squared alpha. Okay. So we're replacing this 1 sine squared alpha with cosine squared alpha. Okay. And so now this is the right-hand side. Okay, so this whole work shows that the left-hand side and right-hand side will be equal regardless of what angle you have for alpha. So this is an identity. But we are going to continue with lecture notes week 12 and 13 on page 10. So we last left off on example 9, part D, which deals with the formulas and identities. So again, it's a good idea to have these handy because we are going to be referring to them back and forth. But verifying an identity means that we're trying to show that the equation will always be true regardless of what x value you plug in. And so what we do is we start on one side of the equation, one side of the equality sign, and then try to arrive to the opposite side by applying some identities. So like in this case, the left-hand side seems to be the one that gives us the most to work with because we do have this sum of angles, which we can try to use maybe like a sum or difference formula or some other type of formula to help us reach the negative sign of x. Whereas on the right-hand side, well, there's not really much we can do with the negative sign of x. Okay, so we're going to start on the left-hand side, which is cosine of pi over 2 plus x. All right, and there's more than one way to approach the problem. In this case, what I'll do is I'm taking a look at the cofunction formulas, which actually looks very similar to what we have. There's this cofunction formula that reads cosine of pi over 2 minus theta is sine of theta. So the only difference between that formula and what we have is the plus, right? We have a plus instead of a minus. But maybe if we rewrite that, maybe if we rewrite it as cosine of pi over 2 minus negative x, okay, which because minus a negative is positive. Now it's going to have a very similar form, except that instead of theta, we'll have this negative x. Okay, so that's the formula that I'll be using, and I'll write it here on the notes as well. So if you're reading back to these, you can take a look at what we use. So the formula is a cofunction formula, and it's the one that reads cosine of pi over 2 minus theta is equal to sine of theta. Okay. And so in order to match it up, so the left-hand side of the equation here is what matches up, except that we have negative x instead of theta. So according to the formula, that should be equal then to sine of negative x, right? Because theta is represented by negative x in our case. So far, any questions at that point? Okay, and then the next thing to notice, or to try and figure out is, well, what is the goal? The goal is to make it to negative sine of x, which we can easily do at this point because sine is an odd function. And since it's an odd function, notice what formula says. If you have a negative in the argument of sine, you can always bring it out into the coefficient, or you can bring it out into just the sign instead of the angle. So this is going to be negative sine of x, and what we're using is the odd formula for sine. And actually, let me be careful here. That wasn't applied at that step. We applied the formula from this step to this step. All right. So questions there? And now that's one possibility. You could have also used the sum formula. So at this point we're done because this is the right-hand side already. But I'm going to show you guys what would have happened if we would have used the sum formula. Okay, so here I'll have option 2. Or again, we're going to start at the left-hand side, which is cosine of pi over 2 plus x. If we look at the sum and difference formulas, cosine of a plus b is cosine a cosine b. And then since we're looking at the top symbol on the left-hand side, that means that we have to use the top symbol on the right-hand side as well. So it would be minus sine of a sine of b. Okay, so I'll rewrite that formula in our notes, and then that's what we're going to apply. is the sum formula for cosine, and it'll be cosine of A plus B is equal to cosine A cosine B minus sine A sine B. Okay, now in our case, on the expression that we're trying to prove, the pi over 2 is the first angle. So let me just color code it. It's the first angle, so that is represented by A in the general formula. And then we have x for the second angle, and that's represented by B in the formula. So if we apply it, that means that we're going to end up with cosine of A, so that'll be pi over 2, times cosine of B, that's the second angle, which in our case is x, minus sine of the first angle again, that would be pi over 2, times sine of the second angle, which is x. All right, so now we can simplify the cosine of pi over 2 because that's something that's on the unit circle. So if we take a look at the unit circle, here at pi over 2, we have a point of 0, 1. So that means that cosine of pi over 2 is 0. Okay, so this is going to be a 0 times cosine of x, and then minus sine of pi over 2. Again, we can look at the unit circle. Here's pi over 2. Sine is always the y value, so it's going to be 1. So minus 1 times sine of x. And then 0 times anything is just 0, so we'll end up with 0 minus 1 times sine of x, which is just negative sine x. And again, that is the right-hand side. So at that point, we're done. All right, so any questions with part D?
So when you say right-hand side, you're trying to get to the negative sine x, but how is that the answer?
So good question. So the answer is not this by itself. It's the whole process actually, because we're trying to prove something. And so that's why I'm not really boxing any part of what we've written out, because in reality, the answer is the whole process. Every single step is it's part of the solution. So that's the actual answer. It's the whole proof is our answer. You guys have any other questions? Let's give part E a try. In this case, we have sine of pi over 6 plus theta plus cosine of pi over 3 plus theta should simplify to cosine of theta. Let me see if I can fix the focus here. All right, so again, in this case, the left-hand side gives us the most to work with because we do have two terms and there are, we have the sum of angles for both sine and cosine. That gives us the opportunity to use some of these sum formulas. So we'll start at the left-hand side, and that is sine pi over 6 plus theta plus cosine pi over 3 plus theta. Now, because it's going to get a little complex, I'm going to color code the terms. And I'm going to start by focusing on the first term, the sine of pi over 6 plus theta. If we look at our formula sheet, we have that sine of A plus B will be sine A cosine B plus, because we use the top symbol on the left-hand side, so we use top symbol on the right-hand side. So plus cosine A sine B. So that means that, again, I'm going to write down the formula. And that is sine of A plus B is equal to sine A cosine B plus cosine A sine B. Okay, so what is that going to look like then? Well, that means in our case, the pi over 6 is like A. So sine of A would be sine of pi over 6 times cosine B, and B in our case is theta, so times cosine theta, plus cosine of A, and A is pi over 6, times sine of B, so that's times sine of theta, because B in our case is theta. And so both of those terms is a result of expanding that sine of pi over 6 plus theta. That means that we still need to bring down this term, the cosine of pi over 3 plus theta, because that we haven't worked on yet. Okay, so now we're going to work on that second term, the cosine of pi over 3 plus theta, by looking at what is the sum formula for cosine. So sum formula for cosine is cosine of A plus B equals cosine A cosine B minus sine A times sine B. So let's write that formula down. We'll have cosine of A plus B equals cosine A cosine B minus sine A sine B. Okay. So these two terms, I'm not going to do anything with them yet, so I'm just going to bring them down. We'll have the sine pi over 6 cosine theta plus cosine pi over 6 sine theta. And then we have plus, so this is the green portion, plus cosine of the first angle, which is pi over 3, so plus cosine pi over 3 times cosine of angle B, and that's theta, so times cosine theta, minus sine of angle A, which is pi over 3, times sine of angle B, which is theta. Okay. And that is the second term expanded. Okay, so from this step, so I guess from this step to this step, this is what we're applying. Okay, now what can we do with that? Well, sine pi over 6 and cosine pi over 3, those angles are on the unit circle, so we can determine what are going to be the sine and cosine. Okay, so pi over 6 is here. This would be the cosine, and y would be the sine. So for sine of pi over 6, we get a 1/2 times cosine theta plus cosine pi over 6, that would be radical 3 over 2 times sine theta. And that is the green part of our expression. The orange part, which is the second term, again, we can use the unit circle to help us. Now we're looking at the angle pi over 3. So here's pi over 3. Cosine of pi over 3 is going to be 1/2. So we're going to have a 1/2 times cosine theta minus sine of pi over 3, and that's a radical 3 over 2 times sine theta. Okay, so questions so far? Now they're all part of the same expression. So that means that we can combine the like terms. So for instance, I have a 1/2 cosine plus a 1/2 cosine. They're going to add up to 1 whole cosine theta. And then we have a square root of 3 over 2 times sine minus a square root of 3 over 2 times sine. Those are going to subtract out to 0, right? They're going to cancel each other out. So the only thing that gets left over is that cosine theta. And well, let's look back at what our goal was. Our goal was to show that this expression was going to simplify to cosine theta. And that's exactly what we've shown with these steps, right? We've shown that it simplifies to cosine theta. So now, because this is the same as the right-hand side, we're done proving the identity. Any questions for that part?
I know you're the professor, but you just make it look so effortless.
No. Well, I mean, it takes a lot of practice, so, you know, don't, I know that sometimes, you know, in class it might seem okay, and then once you actually try it, it's not, you know, it doesn't feel as effortless, and that's normal. So, it's just a lot of practice. Keep practicing, and then you'll have an intuition as to what, you know, what identities to apply.
My issue is I keep forgetting to remove the sine or the cosine if it's another number, like the 1/2. I would have written cosine 1/2 on accident.
I see. So here, maybe like the 1/2 here.
Because cosine pi over 3 translates to 1/2.
Oh, right. This part
But I
here.
would have put cosine 1/2 because I forget to eliminate that it can't eliminate.
I see. Okay. Yeah, so yeah, I would say it's kind of, it's unusual. It doesn't, not to say that it never happens, but it's unusual to get cosine of a half, like to be asked to evaluate cosine of a half. So if you ever see those numbers on your paper as you're working through a problem, that you come across a cosine of a half, always double check and go back, because maybe you just kind of brought over the cosine instead of well, eliminating it with the pi over 3.
Yeah, I'm learning my ways.
Yeah. Okay, good. Alrighty, so let's see. Let's try example 12. In this case, they're asking us to show that sine of 2 theta minus sine of 4 theta will be a negative 2 cosine 3 theta times sine theta. So let's see, both of these we could work with. So I'm going to bring up the formulas and identity sheet. And both of these sides we could work with. So take a moment to look at the identities. Do you have a preference as to whether you want to start on the left-hand side or on the right-hand side? Notice what we have on the left-hand side. We have sine of some angle minus sine of a different angle. And sum to product has that form on the left-hand side. They have sine of an angle minus sine of a different angle. So this is a good option. We could start there. Now let's try that. Start on the left-hand side with sine of 2 theta minus sine of 4 theta. And then we're going to use the formula sum to product. Okay, and so sum to product has sine of A minus sine of B is equal to 2 times cosine of A plus B over 2 times a sine of A minus B over 2. Right, so if we compare against what we have a 2 theta for A, and we have a 4 theta for B. So if we apply the formula, that means that we're going to have a 2 times cosine I'm sorry, guys. Give me 1 second because my kid is curious as to what I'm doing up here. Okay. So this is a 2 times cosine of a plus b. So a we said was 2 theta. B is 4 theta all over 2 times sine of a minus b. So again, a is 2 theta. B is 4 theta over 2. And then if we simplify that, we're going to have a 2 times cosine of 6 theta over 2 times sine of negative 2 theta over 2. And then 6 theta over 2, that we can reduce down to a 3 theta. And then sine, the negative 2 theta over 2, that we can reduce down to a negative theta. So notice we're very close to our goal because we already have the cosine 3 theta. We have a coefficient of 2, not exactly a negative 2, but at least we have that 2. And then we have sine of negative theta, which is not sine of theta, but it's pretty close. What can we do in order to make this look like our goal? We're 1 step away. What is it that we can apply here? What type of function is sine? Is it even or odd?
Odd.
Odd, very good. Yeah, it's odd. So because it's odd, that means that we can bring the negative out from inside of the argument, right? Instead of having the negative times theta, we can have the negative times sine. So if we bring out the negative, we would have a negative sine times the 2 cosine 3 theta. That means I'm just going to bring the negative all the way outside. Okay, so negative 2 times cosine 3 theta times sine of theta. It's kind of like having, if I have a 2 times x times a negative y, I might as well just write it as a negative 2 times x times y, right? So that's exactly what's happening here. I'm not going to place the negative here for fear that it'll look like a subtraction, when in reality it's the product of the negative sign times this. And so that's the reason why I'm deciding to bring the negative all the way in the front. And now that we've done that, it looks exactly like the right-hand side that we were trying to reach. So again, let me just write justification here because I skipped that part. So from this step to this step, we just use the odd formula for sine. So any questions there?
Professor, I have a question.
Yeah.
Are there going to be questions such as these on the exam? Because how would you show that given the platform we have to do it on?
Yeah, so what I would likely do is give you guys a set of options, like maybe like this step, this step, this step, and this step, all scrambled, and I'll just ask you to arrange them in the correct order. And I might throw in there maybe a line that doesn't belong to the proof, and so you would need to know how to pick out the lines that that aren't necessary in order to prove the identity. And so you won't be writing it from scratch. You'll just have to know which lines are part of the proof and which are not, and how to put them in the correct order.
Okay, thank you.
Let's take a look at this part, and for this one, I'm going to let you guys have a couple minutes to try it on your own. But first, I'm gonna get you guys started. So we're going to start with the left-hand side. The left-hand side is sine of x over 2 plus cosine of x over 2 to the second power. And so because there is that power of 2 outside of the parentheses, I want us to take care of that part first, and I don't want the x over 2 to be too much of a distraction. So when you have something to simplify outside of the argument, my tip is to replace whatever complex looking thing you might have here with theta. So I'm just going to let theta be x over 2 for a little bit. That means that we're going to have a sine of theta plus cosine theta squared. And now that it's written in that form, I can think about it as, okay, well, if I have two terms squared, that simply means the two terms multiplied with itself. And if I have it multiplied with itself, then what's the next natural thing to do after that? What do you guys normally do when you see an expression like this and they ask you to simplify? Well, we might want to distribute, right? So we could take like sine and distribute to both sine and cosine, and then move on to cosine and distribute again to sine and cosine. Okay, so from this step forward, I'm going to give you guys about 5 minutes to just kind of brainstorm, and if you want, even write it like on a separate sheet, what you think the next steps are going to be. Keeping in mind that the final answer that we're trying to reach is the 1 plus sine x. Okay, so try to work with this, and then we'll come together in 5 minutes to kind of build the proof together, the rest of the proof together. Okay, but I want you guys to get your feet wet with these types of problems. All right, so any suggestions, or what did you guys get once you distribute these terms out? So if we take sine times sine, that should give us a sine squared theta, right? And then if we take a sine times cosine, will that just give just the sine theta times cosine theta? And then we distribute the cosine. So again, we're going to get a sine theta times cosine theta. And distribute the cosine to the cosine, and we'll get a cosine squared theta. So that means that, well, these two are like terms. We can combine them together. And I'm just going to group the sine squared and the cosine squared together for a second, because that's actually going to lead us to a place where we want to be. But let's see, we first have a 2 sine theta cosine theta. Okay, so questions up to this point. Good. All right, now why did I decide to group these two together? Well, look at the Pythagorean identities. The very first Pythagorean identity says that if you have sine squared theta plus cosine squared theta, that is equal to 1. So that means that these two terms, are going to add up to 1. By the Pythagorean identity. And so I'm just going to write a justification for it. This is by Pythagorean identity. All right, and so that's a step in the right direction, because notice the goal is supposed to have a 1 plus something. It's supposed to be a 1 plus sine x. We're not quite there yet, but at least we have the 1 plus part. Okay, so now let's work with 2 sine, oh, and I forgot the theta, so let me just put that there. 2 sine theta cosine theta. Is there any identity that might help us with 2 sine theta cosine theta? Take a look at the double angle formulas. And we have this double angle formula, sine of 2 theta equals 2 sine theta cosine theta. So we actually have this part, right? We have the right-hand side of the formula. So if we apply it, that means that we'll have a sine 2 theta. So we'll have 1 plus a sine of 2 theta. And that's because this part became the sine 2 theta. Okay. All right, so now at this point, we're even closer to the goal. We have that just one sine of an angle. The angles are different, but that's because initially we had replaced x over 2 with theta. Let's go back to the original variable now, since there isn't really anything else that we can do or that we would want to do, since we're so close to the goal now. I'm going to replace theta with x over 2. And notice if we have a 2 times an x over 2, the 2's are going to cancel, giving us a 1 plus a sine of x. And that is exactly the right-hand side that we were trying to work towards. All right. So questions here?
Yeah, what would you go over that last step again? I didn't quite catch how the x worked out.
Yeah, so what I did was I took theta and I replaced it with what it was representing originally, which was this x over 2. And because there is this 2 that's in front of the theta, that means that we have a 2 times, and I'll do it here on the side, 2 times theta means we have a 2 times an x over 2. And that means that the 2, we can write it as a 2 over 1 times x over 2. And then the 2's are going to cancel, leaving us just with an x over 1, which is the same thing as x. And so that's how we're getting this result out of these 2.
Okay, thank you so much.
Yeah, no problem. Okay. Any other questions with that, with the process? Okay. So that's the last problem that we have for verifying identities. These next 3 examples, or I should say these next 3 problems are all part of this the same example 10, are going to be similar, except that they're asking us to simplify the expression for part A, and they don't tell us what to simplify it to. So it's kind of like proving an identity where you're only given one side of the equation and don't know what the opposite side is. Okay, so what we'll do then is we'll simply try to apply some formulas and identities until the expression looks simpler than what's currently given. Okay. So again, we're going to use that same tip as before because there are squares and a subtraction that's going on. I'm going to forget about the fact that the argument has a 7 times x by replacing it with theta. That way we can focus on the bigger picture and just consider cosine squared theta minus sine squared theta. So if we go to the formulas and identities, is there anything that looks like cosine squared theta minus sine squared theta that you guys can pick up?
Would that be the inverse of the Pythag? Or
So it looks similar, you're right, it looks similar, except that in this case we have a subtraction and there isn't really a way, like if I try to isolate the cosine, it would mean that I would need to subtract the sine squared theta from both sides. So I would end up with cosine squared theta equals a 1 minus sine squared theta, which is not quite the same expression. And I really can't do like cosine minus sine because if I try to bring it to the other side, it becomes a plus, right? So Pythagorean identity wouldn't quite work. Ricardo,
oh, you're
yeah,
right. Yeah, I see it now. It'd be the double angle formula, right?
exactly. Yeah, thank you so much. Yeah, so double angle formula. Look at this first one for cosine 2 theta. It says cosine 2 theta is cosine squared minus sine squared, and that's precisely what we have. So this is going to be cosine of 2 theta by the double angle formula. And I'll just rewrite it here in case you're looking back later on to the notes and don't have your formula sheet. All right. So let's see. At this point, we have only one term, and there's no addition, meaning there's no addition, no subtraction. We don't have a product with some other trig function. We don't have a square. So there's nothing more that we can do. That means that at that point, we want to bring back the original variable, which was the x, or the 7x that was replaced by theta. So this is going to be equal to cosine of 2 times 7x. And that means that we have cosine of 14x. And that's the most that we'd be able to do with that problem. Okay, so that is as simplified as possible. Now, unlike in the other problems that we've been working with, I am going to box this answer because the final expression is our answer. Okay, it's not the process itself, but the final expression that is equivalent to the original one. Okay. Questions here? Let's take a look at part B. For part B, they want us to write sine of 3x in terms of sine of x. And so what that means is it's not that we have to show that sine of 3x equals sine of x, because that wouldn't be a true statement. It's rather that we need to show that sine of 3x can be an expression that involves only sine of x without the 3 attached to it. So that means that maybe we could have like a sine squared of x plus a sine of x, or a 4 times sine of x, or something of that sort, but not the 3 in front of the x. So let's start with that expression, sine of 3x. And it seems like there isn't too much to do here, like too much to work with. So in order to give us some flexibility, I'm going to write the 3x as a 2x plus x. And the reason why I'm writing it that way is because then we can apply the sum formula for sine, right? Now we can do like sine of a plus b. So I'm just going to rewrite the formula here. Sine of a plus b is equal to sine of a cosine b plus cosine a sine b. And in our case, we have a 2x for a and an x for b. So if we apply the formula, that means that we have sine of angle A, that's sine of 2x, times cosine of angle B, so that's times cosine of x, plus cosine of angle A, so that would be cosine of 2x. Ooh, and I didn't leave myself enough room, so let me just shift this over. Okay, and then finally times sine of angle B, so that would be sine of x. Okay, so even though it looks a little more complicated now, it's a step in the right direction because we're supposed to end up with something that has only sine x's in them. And at least here we've introduced one of those terms, one sine x. We still need to work with the sine of 2x, the cosine x, and the cosine of 2x. But that's, well, of course, what we're going to be working with now. And so I'm going to color code these factors again. All right, and then let's start with sine of 2x. If you look at the double angle formulas, we have a sine of 2 theta is equal to 2 sine theta cosine theta. So it's similar to what we have. In fact, it's the only difference is the variable that we're using. So this is actually going to be equal to 2 times sine of x cosine of x, okay, just this green part, by the double angle formula. And then we have, I'm going to bring down the rest of the term, so times cosine of x plus cosine of 2x times a sine of x. I'm just going to make a comment here. From that step to this step, we're using double angle formula. For sine. Okay. Now, what does that mean? That means that we can multiply these two together to simplify. So we'll end up with a 2 sine x times cosine squared x And now I'm going to focus on the cosine of 2x and see what we can do with that. So cosine 2x are also double angle formulas for cosine. It would be the cosine 2 theta, and there's more than one. Now, because we want an expression that has only sine of x, or if we're thinking about this formula as only sine of theta, the third one would be the best option, because the third one has 1 minus 2 sine squared theta, whereas the other ones contain a cosine. Okay, so I'm going to choose this third formula for it. So that means that we're going to have a 1 minus 2 sine squared x, and then we still have times sine x. And I have to be careful here because since I have multiplication with two terms, I need to have parentheses around it to make sure that the sign gets distributed to both of the terms. Okay, so that's the result of applying double angle formula to cosine 2x. All right, so let's see where that is going to lead us. I'm going to distribute this sign here. So let me just bring down these terms. Those we're going to keep the same for now. And we're going to have a sine x times a 1, so that'll give us a sine x, minus a 2 sine squared x times sine x, so that's minus a 2 sine cubed x. All right, so notice we're really close now because we do have only sine here. Okay, don't let the the superscript of 3 kind of throw you off. That really just means that it's sine of x raised to the third power. Okay, so it's still just sine of x. So this looks good. This looks good. This part looks good. The only thing that we need to worry about now is the cosine squared x needs to be rewritten so that it involves only sine. So how can we do that? Any ideas? So look at what we mentioned earlier about Pythagorean identities. We tried to apply it to one of the problems, but it didn't quite work in our favor. But now it might actually help us a bit because when we solve for the cosine squared, that gave us a 1 minus sine squared theta. In our case, we have an angle, we have a variable of x, which we can replace for theta. So this is going to be a 2 sine x times a 1 minus sine squared x. And again, I'll color code this. I think I've already used all of my colors before, so I'll start over. I'll use orange again. So the cosine squared becomes this 1 minus sine squared, and that's by the Pythagorean identity. There's the one that says cosine squared theta equals 1 minus sine squared theta. And then I still need to bring down these two terms. So plus sine x minus 2 sine cubed x. All right, and now we'll distribute because we have a parenthesis and a difference in the inside, so we're going to distribute whatever's outside. So 2 sine x times 1 will give us 2 sine x. Then 2 sine x times a sine squared will give us minus 2 sine cubed x. And then bring down the plus sine x minus 2 sine cubed x. We're almost done. We can combine like terms now. I have a 2 sine x plus a sine x. That's a total of 3 sine x's. Then we have a -2 sine cubed x minus a 2 sine cubed x. So that's a -4 sine cubed of x. And at this point, we have an expression that involves only sine of x, because again, this is the same as 3 sine x minus 4 times sine of x to the third, right? So we only involve sine x, which means that we are done. And this expression here is our final answer. Any questions there? Okay. Part C. For part C, they want us to write sine of 2 theta minus sine of 4 theta as the product of two functions. We actually just did this problem, except that in the other version that we saw, they gave us what it should simplify to. And here they just tell us it has to be the product of two functions. So again, let's look at our formula sheet. We have sine of an angle minus sine of a different angle. If you look at the sum to product formulas, we have the sine of an angle minus sine of a different angle is equal to the product of cosine with the angles manipulated times sine with the angles manipulated. So this is the formula that we're going to use here. Let's just write that down. Sine 2 theta minus sine 4 theta is going to equal something, and that something is going to be given by whatever the formula tells us. And the formula is sine of A minus sine of B is equal to 2 times cosine of A plus B over 2 times sine of A minus B over 2. Oh, sorry, that's a little crammed in there. All right, so let's see. A is like the 2 theta, and B is like the 4 theta. So we're going to have 2 times cosine of 2 theta plus 4 theta over 2 times sine of the difference. So sine of 2 theta minus 4 theta over 2. And that's going to give us a 2 times cosine. Again, 2 theta plus 4 theta is 6 theta, and 6 divided by 2 is 3. So we'll have 3 theta times sine of 2 theta minus 4 theta is negative 2 theta, and then negative 2 divided by 2 will just give us negative 1 theta. We have that. And then finally, we saw in the previous problem, sine is an odd function, so we can bring the negative outside, and when we say outside, we mean we'll bring it all the way to the front. And so it'll be a negative 2 cosine 3 theta times sine of theta. And at that point, we have the product of two functions, right? It's the product of cosine and sine. And so we've met the requirement of the problem. Any questions there?
Would you explain the directions again for C? Like, what is the product of two functions? Because I'm thinking I need to add something, and that would be my final answer.
Yeah, so product means multiplication. So what they're saying is find an expression that is the multiplication of two functions. And when they say two functions, since we're talking about the trigonometric functions, that's what they mean. It means it could be either be like sine cosine or tangent cotangent or something like that. But in this case, it turns out to be cosine and sine, simply because of what's given to us. But when they say product, it means multiplication of two functions.
Okay, thank you.
Mhm. All right, and now we'll take a look at an application problem. So we're going to see the relevance of these identities as applied to, this is kind of like a physics problem. Okay, so example 11 reads, according to Lambert's law, the intensity of a light from a single source on a flat surface at a point P is given by I equals, and my printer didn't do a very good job of printing that, but it's I equals K times cosine squared of theta. Again, this would be theta, where K is a constant. Part A is write I in terms of the sine function. Okay. So before we even go into that, I just want to give you guys just a little diagram to have some insight as to what this is representing. And so it's talking about the intensity of light from a single source. Okay, so let's say that you have like a flashlight and you turn it on and you are lighting up a flat surface. We'll say it's a wall. It's a flat wall. And there is a point on the wall. We'll call it P. And it's saying that the intensity of the beam of light at that point is going to be a constant K times cosine squared of the angle theta. Now the angle theta is referring to the angle that gets formed between the horizontal ray of light and the ray of light that's pointing at the point P on the surface. So that's what it's referring to. All right, so we'll keep that in the back of our minds. Let's look at part A. Write I in terms of the sine function. So we need to apply our formulas and identities to get the cosine squared theta to look like something that involves sine. Okay. So again, any ideas or any suggestions as to what we might be able to use or replace cosine squared theta by so that it involves sine instead of cosine? Well, we're actually going to use the same Pythagorean identity that we've been using for the other problems. The one that says cosine squared theta is 1 minus sine squared theta. Okay, so we're going to say this is K times 1 minus sine squared theta. Again, I'll write the justification on the side. This is by Pythagorean, excuse me, by
Bless you.
Pythagorean, thank you. Yeah, by Pythagorean identity, the one that says that cosine squared theta is 1 minus sine squared theta. Okay, so we're almost done with it, except we need to distribute the k. K times 1 will give us k, and then k times sine squared will give us k sine squared theta. And so that'll be our final expression. I equals k minus k times sine squared theta. All right. Now part B is asking, why does the maximum value of I occur when theta is 0? Okay, well, let's see. We'll look at the original expression and this second expression that we found. If we plug in theta equals 0 into the first expression, we're going to get I is equal to k times cosine of 0 and then squared. So that means cosine of 0 is 1, so it'll be a k times a 1 squared, which is just k. Okay. Now, if we think about what is the maximum value that cosine can attain, well, think about the graph. Okay, on the graph, the original cosine function begins at the tops at some value here on the y-axis and then goes down and then comes back up. Do you guys remember what was this original y value for cosine x? Where does it begin? Well, it begins at 1, right? At 0, 1, and the lowest it goes to is a -1. So the maximum that cosine attains is 1, and it happens when the angle is 0. Okay? So that is why I attains a maximum at theta equals 0, because k is a constant. That's not going to change. But theta, cosine theta, the value can change depending on what theta is. And the maximum it'll ever be is a 1. And that happens when theta is 0. Okay, so we're going to write that down. So I equals k times cosine squared theta attains a maximum at theta equals 0. Because cosine of angle theta reaches its maximum y value, or its maximum value of 1 at theta equals 0. For any other value of theta, that angle is going to start decrease. The cosine of the angle is going to start decreasing to something that is less than 1, and then to 0, and then to something that's negative. It won't reach 1 until it's again at 2 pi radians. Right, now let's see if that agrees with our intuition, because this has a practical application. Right, so let's see what that means. Think about it when you've held a flashlight and you've pointed it at any surface. Where is the brightest spot on the surface?
The center?
At the center, very good. Yeah, at the center. So the center is going to be directly in front of the flashlight, right? So it's like the point P is down here. Now, if the point P is directly in front of the flashlight, that means that the angle doesn't even open up, right? It just stays there. And so that means that the angle has a measure of 0 radians or 0 degrees. It didn't open. And so that, okay, according to what we're seeing here, that gives you the maximum intensity. So that is why we see the brightest spot in the center, because it actually agrees with this formula, which says that at 0, you're going to see the brightest spot. Now, when, according to this formula, should we basically see no intensity, an intensity of 0? Well, intensity of 0 would happen when cosine of theta is 0, meaning at this point. And when do we see cosine of theta being 0? Well, that's going to happen at pi over 2. And pi over 2 is like 90 degrees. So let's think about what that means in terms of the picture. In terms of the picture, an angle that is 90 degrees would be here. And that's 90 degrees, pi over 2. And so what that is saying is that if the point is directly above the flashlight, you're not going to see any intensity here. You're not going to see this point being lit up because the flashlight is beaming towards the wall in front of it. So if you try to come here, you're not going to see any intensity.